The Argand diagram is what we're going to look at. We know we can place real numbers on the number line, but how do we visualize complex numbers? And that's where we have the Argand diagram. It looks very familiar. It looks just like the Cartesian number plane. So we have an x-axis and a y-axis, but technically what we actually have is a real axis. There's your number line, and that's why the number line is horizontal, by the way, because it's actually the x-axis. And that vertical one becomes the imaginary axis. So if I want to plot the number 2, no different to what we've been doing since, when's the first time you plotted numbers on a number line? Maybe primary school, maybe even infants, but you just, oh, there we go, we'll put it on 2, there it is. Now if I have a purely imaginary number, so negative 3i, I can do the same thing but on the imaginary axis. I'll place it down there. Ones that are a mixture, well, it becomes just like plotting coordinates. It's minus 2 along the real axis and then 1 along the imaginary axis, so we plot the point negative 2, 1. 4 minus i, 4 along the real axis, negative 1 in the imaginary axis, and there it is down there. 4 plus I, 4 along the real axis, 1 in the imaginary. Now this brings up an interesting thing. What we should find then is conjugates will always be reflected in the x-axis. Because remember it's plus or minus. What about this one? Negative 4 plus I. Okay, it ends up over there. And this brings up another interesting one. If you find the negative of the number, then what it should be is a reflection through the origin. So you go diagonally through the origin, and that's where the negative of that number should be. This explains why, with square roots, you end up with plus or minus a certain number. The square root of, well, seeing 2 is plotted, let's talk about 2. If I said, x squared was 4, so what's the square root? Well, it's 2, but if I reflect through the origin, negative 2. There's your 2 answers. And that's true for all square roots. Multiplication by I is very important. So 1 plus 4i, let's plot it. So we plot 1 plus 4i, and it turns out to be a rotation of 90 degrees. So when you multiply by I, you get a rotation of 90 degrees. If you were to multiply by another I, rotate another 90 degrees. But what have you done? You've multiplied by negative 1, and there's the 180 degrees. And that's why the negative was a reflection through the origin of 180 degrees. But every complex number has a unique position on that Argand diagram. There's only one complex number that can be represented by any single point. So now we can talk about pictures or locus, however you want to say it. But in terms of complex numbers, rather than what we're used to seeing, the Cartesian equations, let's start with some basic ones, just horizontal and vertical lines. So here's a horizontal line, which in the Cartesian terms we would say y equals a constant number. But when we talk about complex numbers, we say, well, what do all these points have in common? And it's their imaginary part. Every point on that line has an imaginary part of c, which is exactly the same as y equals c if you think about it, because y is the imaginary part. But we could give it this equation then. The imaginary part of z is equal to c. That would be the horizontal line. And similarly, with a vertical line, those ones all have the same real part. So the real part of z is equal to k. Circles, there's our basic circle centered at the origin. Well, remember the equation of a circle centered at the origin would be x squared plus y squared is equal to the radius squared. But what have we now seen about x squared plus y squared? It's the sum of 2 squares, which we now know is a number times its conjugate. The circle then could have the equation z times z conjugate is equal to the radius squared, instead of saying x squared plus y squared is the radius squared. Find and describe these ones then. What would this look like? Is the question. What would this look like? Now if you don't immediately recognise it, expand out, maybe something will happen. If I expand all this out, I'll get z conjugate plus 4 plus I z conjugate and so on. Difference of 2 squares at the end there. And after manipulating it round, I'm still not got an idea what it's going to be, so I'll bring it back to x and y. So maybe I'll recognise the Cartesian equation. So eventually when I sub all that in, I get x squared plus y squared plus 8x plus 2y plus 16 plus 1 is 49. Hang on, it's a circle. because here's x squared plus y squared. So let's play with it to get the equation of the circle. And there it is. X plus 4 squared plus y plus 1 squared is 49. So alright, the locus of this one would be a circle, centre at -4, -1, radius 7. So we can always jump in between the two. If we don't recognise it when it's written in complex form, go back to the real and imaginary parts and see what the Cartesian equation is. And then that'll tell us what it is. Generally, if you see this sort of thing, because this is what we've got here, if you look at it closer, if you've got z minus some complex number, times by the conjugate of z minus the conjugate of that complex number, and that's what we've got here. So you've got z plus 4 plus I, conjugate of z plus 4 minus I, which is the conjugate of 4 plus I. It's going to be a circle, and the radius would be, of course, r. This one here, wow, 1 on z plus 1 on the conjugate of z is equal to 1. Again, I really don't know. So let's play with it. I'll multiply everything by the denominator. Maybe something will pop out. I get the conjugate plus z is equal to z times z conjugate. Yeah, still not 100% sure there. So I'm going to put it into Cartesian form. Z plus z conjugate I know is twice the real part. So I'm talking about Cartesians, that's going to be the x value. So 2x, z times z conjugate, there's our good old sum of two squares. I got a circle again. Now let's play around with it. There it is. X minus 1 squared plus y squared is equal to 1. Locus is a circle, centre 1, 0, radius 1 unit. So we would think, because there's something else happening here. You've always got to go back to what the original question was. I transformed it into something else so I could recognise it. But there's a little issue. And we still have that rule. You cannot have 0 on the bottom of the fraction. So it's not actually possible for 0, 0, the origin, to be a solution to this. Because if I was to substitute in 0, I would have 1 on z. Well, z is 0. No, I can't do that. But even the other fraction, 1 on the conjugate of z. Well, conjugate of 0 is 0. Still got the same problem. So you always need to refer back to the original and say, hey, are there going to be any exclusions in our domain? Things like that. Now, it is pretty close to the circle we're thinking of, but there's a point discontinuity there at the origin. That would not be included in that picture. We're going to look at locus in a lot more detail in, I'm not sure how many lessons it is, but yeah, this is just a brief taster, I guess, of that idea. So, exercise 1C, let's add those to our list.